Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 50, part B, and we are discussing the central limit theorem, and this is part 2. Last time we talked about the central limit theorem. We did not do an example, but we did talk about the convergence of x bar, and we talked about the sufficient size of n. So in this video, we're going to do some examples, and then at the end, there will be some links on the Moodle webpage to Khan Academy videos for you to watch. So last time we finished up about here, and so we're going to do this first example. We're going to now you'll notice that this doesn't match up with what's in your textbook. And again, instead of using 20 or something, I'm using our standard of 30. So that if you see n greater than or equal to 30, CLT is okay. And CLT is central limit theorem. So let x1, x2 up to x30 be a random sample from a uniform distribution, uniform between 0 and 1, and just in case you're wondering, it's continuous. Okay? So we're going to define y equal to x1 x plus x2 plus ... plus x30. Find the probability that y is less than or equal to 9.1. So now remember that the expected value of the uniform distribution is a plus b over 2, where if we draw this out, here's a, here's b, and so the mean is halfway between a and b. Okay, so mu is a plus b over 2. A here is 0, and b is 1. So our mean is going to be a half. The variance is going to be b minus a squared over 12. That is 1 over 12. That's 1/12. Okay. So by the central limit theorem, we have that the probability that y, and I guess I took this from 9.1 to 14.1. I changed it. I apologize. So y is less than or equal to 14.1. That is equal to... Now, what we're going to do is we're going to transform this using w is equal to x bar minus mu over sigma over the square root of n, right? But now, let's look at this. You're going to see that x bar, so the sum of xi is equal to n times x bar, okay? So remember that x bar is equal to 1 over n sum of xi. And so if I solve for the sum of xi, which is what y is the sum of xi from I equals 1 to 30. So this is going to be n times x bar, okay? So if I take n on the top, so if I take n here times n, if I do that, then I have multiplied by 1. And when I do that, I end up with the sum of xi minus n times mu over the square root of n times sigma. Okay? So this is the transformation that I'm going to use. And remember, we're calling the sum of xi y. So I have y minus n times mu over the square root of n times sigma. And so I take 14.1 minus n, which is 30, times mu, which I found was 1/2, over the square root of n, which is 30, so the square root of 30, times the square root of 1/12. And this comes out to be a negative 0.5692, etc. So for my z-table, I'm rounding that to a negative 0.57. And phi of 0.57 from table VB, where we look up the positive 0.57, is equal to 0.2843. I'm not going to the z-table because we've already gone over how to do that. So now we're going to look at page 209 in the book, and the graphs are on page 210 of the 10th edition. Now, I don't have an ebook of the 10th edition, I have the 9th edition, so we'll take a look at that in a minute. Let x bar be the mean for a random sample of size n equals 30. So again, I increase this to n equals 30 from a distribution with a PDF of x cubed over 4. And x is between 0 and 2. So I have graphed this. Again, I'm going to always encourage you to graph it if you can. So I've plotted some points here for x equals 1. I plug that in, I have a fourth. And so then for x equals 2, I have, it's 2. 2 cubed is 8, divided by 4 is 2. So this is supposed to be, oops, sorry about that. Sometimes it jumps when I touch the edge. All right, so let me zoom back out a little bit. Now mu is going to be, so we want to find mu, we want to find the variance, and we want to find eventually the probability that x bar is between 1.5 and 1.65. And we're going to use the central limit theorem. So we weren't given the mean, so we have to figure out the mean. We were given the distribution function, the PDF, so we can figure this out. So remember that the mean is x times f of x dx from negative infinity to positive infinity, but the support of x is between 0 and 2, and so every other bit of the integral is going to be 0 because f of x will be 0 outside of the range 0 to 2. Okay? So we substitute in, and I have substitute this in incorrectly. So great. All right. So this is x cubed. This is supposed to be, oh no, it's not. I did it right because I forgot that I have an x here. So I should have written out x times x cubed over 4 as a step, and then I would not have forgotten that I needed to multiply by x. Great. So I didn't make a mistake here. Good. So x to the 4th over 4, I integrate that. X, I add 1 to the 4, it becomes 5. X to the 5, I divide by the 5. So 5 times 4 is 20, and so I have 1 over 20 times x to the 5th. When x goes between 2 and 0, I plug in 0, I get 0, so I plug in 2, I get 32/20ths, or 8/5, and in this case I'm certainly going to write it as a decimal since it's a non-repeating decimal for this problem. You could leave it as fractions, but I like to do that when I'm talking about probabilities, and this is not a probability, this is a value, and we're going to be looking it up in the normal distribution table, so I'm going to need decimals in the end. So now if this was a repeating decimal, I would leave it in this form until I got to the end, so I would have less error. But since it's an exact decimal, we could use that. Okay, and so I take ex squared. So this is x squared f of x, so this becomes x squared times x cubed over 4, which is x to the 5th over 4 dx. This goes from 0 to 2. I shouldn't forget that. That's going to give me x to the 6th over, so 6 times 4 is 24. 2 to the 6th is going to be 64 over 24. That's 8/3. Now that is a repeating decimal, so I'm not going to get rid of that. To calculate the variance, I'm going to use fractions. So I have ex squared minus ex, quantity squared. So 8/3 minus, let's see, so 8/3 minus 8/5 squared. So 8 squared is 64, 5 squared is 25. My common denominator is 75. I end up with 8 over 75. Okay, so 8 over 75, 8 divided by 75 is a repeating decimal. Let's see, so 8 divided by 75, and that's 0.10666666. Okay, and so that is my, so I'm not going to simplify this, but I can use 1.6 for the mean. So I need those two numbers. And so the probability that x bar is between 1.5 and 1.65, since n is greater than or equal to 30, I'm going to use the CLT, central limit theorem. And so I convert this. I subtract the mean, which is 1.6, and I divide by the square root. I could put all of this under the square root, but I haven't. So I put the, so sigma is equal to the square root of 8 over 75. So I have the square root of 8 over 75 divided by the square root of 30. So this would be divided by the square root of 30. I can rewrite this as the square root of 8 over the square root of 75 all over the square root of 30. This is 30 over 1. I invert and multiply, and the square root of 30 goes on the bottom. And that's what I have here, 75 times 30. Okay, and so so I wrote it out here, and then I shortcut, or I combined a little bit there. And so when you work this out, we get to two decimal places, negative 1.68 and positive 0.84. So phi of 0.84 minus phi of negative 1.68. Remember, this is going to be in table 5b. I'm going to look up positive 1.68. This is going to be in table 5a, and I'm going to look up the 0.84. Okay? And so I can get these two values directly from the table, and it ends up being 0.7530. So we have just gone back to what we did in the earlier section with the normal distribution. I think I mentioned before, the normal distribution is the most important distribution in statistics. It comes up the most often. Behind that, I would say, is the t-distribution. That's not saying that the other distributions aren't important and they don't occur, but when you talk about statistics, we spend a lot of time on the normal distribution. And the central limit theorem means that anytime we're taking a random sample, we have the potential to have a normal distribution. All right. So in the next part of this will just be the links to the Khan Academy videos. Please take a look at those. Make sure that you understand the concept of what's happening with the central limit theorem. That's it for this video. Please don't forget to scan and upload your lecture notes before midnight of the date listed in the course calendar. If you have questions, come to virtual office hours. If you need an answer before you can come to virtual office hours, email me. But please email me a picture of the problem, because I may not have it available, and a picture of your work so I can see how you're approaching the problem. And I'll be happy to point you in the right direction. Please take care of yourself, stay safe, and we hope to see you next time.